session, after coffee session. Our first speaker is Yang Lu.
Hi, everyone. So today I'm going to be telling you about some recent progress or recent works on dynamic graph algorithms. So I guess over the last several years, including the last year when I was a member here at the IS, I've worked a lot on graph algorithms, and I just want to tell you a little bit about some. So I'm going to broadly talk about two problems in this. The first is going to be a problem called incremental cycle detection, and then I'll talk about a problem called the dynamic matching problem. So the problem of incremental cycle detection is one of the simplest to state problems that is on a graph that's changing over time. Initially, we have an empty graph, and then during each time step, a directed edge arrives and it gets added to the graph. And then an algorithm should decide whether that graph has a directed cycle or not. So naively, what you could do is after each step, you just recompute on the whole graph whether there's a cycle, and then do this m times. But the question is, can you do better? Just to make sure we all understand the problem and what a dynamic graph process is in general, initially empty graph, and edge arrives, there's no cycle. So the algorithm looks, no cycle, looks again, no cycle. And this keeps happening, there's still no cycle. And finally, an edge gets added that creates a cycle. And at this point, the algorithm should say like, okay, I found a cycle, we're done. So this problem has been studied a lot over the last several decades. And the best runtimes that were known for processing m edges arriving into the graph was the min of m to the 4/3 and n squared. The best you could hope for is m, because that's the total number of edges that's arriving. And the question is kind of, is that achievable? Now, these type of runtimes were achieved by some very nice combinatorial ideas. So just to give a little bit of a taste for what they're like, a lot of them rely at a very, very high level on the following nice fact. If I have vertices that are in a cycle, if vertices u and v are both in the same cycle, then the set of ancestors and the set of descendants of u and v are the same. So these algorithms somehow do some kind of partitioning, random partitioning of the graph based on ancestor and descendant relations, and then look in these clusters to try to find cycles. And hopefully these clusters are smaller, so it's easier to find the cycle if it exists. Very high level, that's kind of what it does. Now, last year in work that was actually done while I was a member here, we gave an algorithm that solves this problem in time m to the 1 plus little o of 1. So up to this little o of 1, it's kind of the best possible you could hope for such a problem. And it also extends to maintaining something called the strongly connected components in a graph. Basically, u and v are in the same strongly connected component if they're involved in a cycle. So the interesting part about the algorithm there is that it deviates quite far from previous combinatorial approaches. So I'm just going to state a little bit about kind of how we look at the problem. So to look at it, we actually study a problem that's far more general than incremental cycle detection. We study a problem that is basically dynamic minimum cost flow under edge insertions. So here, once again, you have a directed graph, and I'll just explain what a minimum cost circulation is. So you have a directed graph, every edge has a capacity, just like a total amount it can support, and a cost, which is the amount it costs to put one unit. And the minimum cost circulation problem asks to find a circulation in the graph, which satisfies the following properties. Circulation means that when I assign a real number to every edge, this assignment of real numbers satisfies that the total incoming and outgoing from every edge is the same. That's what it means to be a circulation. And these assignments satisfy the capacities. They're non-negative, and they're at most the assigned capacity of the edge. And finally, you want to minimize the cost over all such assignments. So instead of studying this incremental cycle detection problem, what we actually do is study the much more general incremental, we call the threshold min cost flow problem. This is as edges arrive into a graph, and there's some fixed threshold f that's given at the start, you want to decide what is the first instance that the minimum cost circulation has cost at most capital F. So you can see that this kind of captures minimum cost. This captures the cycle detection problem, because if a graph is no cycle, then there is just no circulation. So the best cost is 0. But as soon as there's a directed cycle, then there is a circulation, and if you assign cost properly, it will be like negative cost. So this is a vast generalization of that. And what we prove is that kind of this problem can be solved in the same runtime, m to the 1 plus little o of 1. Now, once again, just to highlight that these are very much not combinatorial approaches, this algorithm builds on a long line of work that gave a m to the 1 plus little 1 time static algorithm for minimum cost flow. So like basically minimum cost circulation on graphs that aren't changing. Turns out those ideas extend to dynamic graphs in some natural way with some additional work. And once again, these methods are not combinatorial. They actually use tools from convex optimization. For example, the interior point method for linear programming, or some version of it. And I just wanted to mention as a final word on this problem that our algorithm or some adaptation of it also works when edges are being deleted. So we call this the decremental setting. So like incremental means only edges are added, decremental means only edges are deleted. If you allow for both insertions and deletions, there's various reasons that it's probably impossible. But I won't get into that.
There's one question. When you
Yes.
say something like that, you mean that you don't know a priori the order of deletions and the order of insertions, right?
Yes, it's just,
Okay.
yeah, like deletions mean you get some graph and then over time edges get deleted, but you don't know the order. Cool. So now that that's settled, I'm going to talk about this dynamic matching problem now. So in the dynamic matching problem, you have a bipartite graph G. In this case, we are going to allow it to undergo both edge insertions and deletions, like interleaved, okay? And the question is, can you maintain a 1 minus epsilon approximate maximum matching in the graph with, some runtime? There's been several results on this problem over the last several decades. And I guess maybe instead of going over them one by one, the upshot is that it's really unclear whether you should expect that there's an algorithm that does better than a runtime of about n per update, where n is the number of vertices in the graph. There's various reasons that n is achievable, but I won't get into that too much. So I guess just as a motivating question for the last segment of the talk, I want to ask, should we expect that there's an algorithm for dynamic matching that has the following runtime? Basically n to the 0.99, so like a little bit sublinear in n, and then polynomial in 1 over epsilon. Should we expect that this is possible at all?
So you want to construct a matching or no, it exists only?
Let's do construct. Exist is also a good question, but let's do construct. Yeah. Now, in general, in complexity theory or algorithms, we have very limited techniques to prove that problems are hard. So there's been a recent line of work called conditional hardness. In the general idea is you assume that a few problems are hard, and you try to use the fact that those are hard to deduce that other problems are hard. So there's a couple classical assumptions. For example, this three-sum problem, strong ETH and APSP. So APSP is finding all pairs of shortest paths in a graph. Strong ETH is there a faster algorithm for solving SAT, like satisfiability? So a particular hardness conjecture that's been proposed and has been very nice for working dynamic graph problems is this online matrix vector problem. So I'll try to explain what the idea is behind this. In this problem, you're over the Boolean, you're considering Boolean matrices, and you're given a Boolean matrix M up front, okay? And then now we go for n time steps, and during the ith time step, you get a vector vi, which is again a Boolean vector. Now the question is, after you get vi, I have to find m times vi, the Boolean product. And the conjecture is that over these n steps, it requires about n cubed time to find all these products mvi. And this would basically be the best, this would be the kind of the naive bound because, well, finding each mvi could take n squared naively. So n cubed is the kind of the naive algorithm. And the conjecture is you can't do better. If you want to think more graph theoretically, here's an alternate formulation. I give you a bipartite graph initially, given by its edges. And then during each query, I give you a subset AI of the left and BI of the right. And the only question I ask is there some edge in AI, between AI and BI in the graph? once again, you could do it in n squared time just by checking all the pairwise edges, and the question is, can you do better?
One question, why is it called online? Where's the online part here?
Uh,
Giving me all the data.
Yeah, you only get the next vector vi plus one after you respond to vi.
Because if you were giving me all the n at the very beginning, it would be strictly easier.
Yeah, I'm gonna say a word about that, yeah. So, okay, so now now why is it called online? The reason I called it online is if you were given all the vectors v up front, what you can do is throw all the vectors v into a large n by n matrix, compute the matrix, like the product of the m and the v matrices, and you get a faster algorithm. So the kind of the conjecture is that if I'm forcing you to solve all these problems online, then you can't do better than just kind of each thing naive. Okay, should we believe this conjecture? Well, I don't really know. But okay. As possibly a counterpoint that like makes this conjecture not seem that feasible, or it's at least kind of sketchy, is that there is a randomized algorithm that has the following total runtime: n cubed over 2 to the square root log n. And while I'm not going to get into how this works, it's kind of based on various algebraic techniques, like, yeah, but it's based on algebraic techniques. So in the connection to dynamic matching, in some work I conducted at the IS last year, I showed some kind of connection between dynamic matching and some approximate version of this online matrix vector problem. And as some corollaries, there's an algorithm for dynamic matching with the following runtime. So still not really better than n, but like you save a 2 to the root log n factor. And to get this, you use this algebraic OMV algorithm that I mentioned on the previous slide as a subroutine. So that's all I had. Thanks.
Questions for you?
Yeah, so in your first problem where you add directed edges, could you also consider the problem where you would add edges and vertices? Because at first you start with a fixed set of vertices.
Sure.
Add vertices.
That's fine, yeah. That's fine because you can kind of assume you just had a lot of 3 vertices at the front and like, so that's also. Sure.
At a certain point, you mentioned that you can also maintain the strongly connected components adding edges.
Yeah.
Then what does it actually mean? Like, then if you maintain the structure, then I can ask you, is this vertex and this vertex in the same component? What kind of?
So like initially every vertex is in a different component. As edges are added, components might merge. So you can actually just kind of explicitly maintain a representation of all of them. Yeah. Was there anything else?
I have a philosophical question. You seem to have more classes than I was expecting. I was like this P, NP. Why did you say many more classes of difficult?
Okay, good. Yeah. So in general, this is something called fine grained complexity, which is you're interested in understanding which problems take time n cubed versus n squared.
That's not the exponential versus polynomial.
Yeah, it's within polynomial time, and then there.
Okay.
Yeah.
I got it.
Questions? Okay, well, thank you very much.